Hi, folks. Thanks for coming. I'm going to tell you about quantum diamonds today. First, would you like a diamond? Do you think that's real? And it's worth like $1 billion. Would you like to take it? It's actually a fake one, but you can play with it, maybe hand it around. So my name's Ron Walsworth, and I'm a professor at Harvard, so that involves teaching and research. But today, I'm going to tell you about diamonds. Diamonds. We all know of diamonds as gemstones. Beautiful, crystalline diamonds, very hard, expensive, cut into wonderful shapes for rings. But many diamonds have defects in them, atomic scale defects that can give them colors like you see here. Blue, green, pink. And in particular, the pink diamonds I'm going to talk about today have quantum properties that are, in the end, interesting and quite useful. I'll tell you a lot about them. So what are the quantum properties, and what are these defects at the atomic scale in pink diamonds? Well, look at that little cartoon I have up there. That's a lattice of carbon atoms in gray that make up the diamond. You can pass this around too if you'd like, where now the black indicates the carbon atoms in the diamond lattice. But you see there's an N and a V. The little red N is a nitrogen atom, which has replaced one of the carbon atoms. And the little white V is a vacancy. It's a missing atom. So one of the carbon atoms is missing. And defects like that occur naturally in diamonds that you might dig out of the ground once in a while and occasionally make them pink. But we can also grow diamonds in a laboratory that purposely have these so-called nitrogen vacancy color centers in them. So there's the carbon atoms, and there's these nitrogen vacancy or NV color centers that make diamonds pink. They absorb green and bluish light, and there you go, there's the nitrogen, there's the vacancy, and they emit red. So diamonds can be made pink. Okay, that's kind of neat. But they have special quantum properties, and I'll list a few of them for you here. One, remember this absorbing the green light and emitting the red light? Well, they emit red light as individual packets of light known as photons. They're quantized, they come in discrete amounts, and they emit them one at a time. So get ready. You like that animation? That's about as fancy as this talk is going to get here, okay? But, there they go. It's emitting these photons one at a time. And you can count them. Here comes one photon, then another, etc. So that's one of the quantum properties. They also have a property called spin. Around the nitrogen atom and the vacancy are electrons, which have an property called spin. It's a quantum mechanical property that's associated with having angular momentum. And the pink circle or oval I put up there is just indicating that spin where it's localized, and they see the red arrow, that's the kind of spin. It can point in one direction or it can point in another direction, up or down, quantized. And spin is sort of like a magnet. And in fact, the magnets that we know and love are made up of many electrons inside that have spin, typically, and give them those magnetic properties. They make magnetic fields, and they're sensitive to magnetic fields. So if the spin is pointed in that direction, you might have the magnet be a north pole pointing in that direction. And if you reverse the spin, its direction of the magnet changes. Okay, so it's a little magnet at the atomic scale. It's emitting one photon at a time. But there's another key property. If the spin is pointing in that direction, it emits photons rapidly. They come out fast. Whereas if you reverse the direction of the spin and the magnet, now they're coming out slowly. Okay, so that means if you could collect the photons and see if they're coming fast or slow, you could tell which way the magnet is pointing. So remember that. That's going to be the key elements. These NV centers absorb optical light, they emit in the red, and they either emit a lot of light fast if the spin and the magnet's in one direction, or slow if it's in the other direction, okay? So these are the quantum properties of these quantum diamonds. Yeah, that's a nice cartoon. In reality, in the laboratory, what does one of these things actually look like? It might be something like that. Come in different shapes, glowing all red because we're hitting it with a green laser right there. Okay, great. So what? It makes the diamonds pink. Why should you care? Well, I'm going to tell you a little bit of a history story about how this field got going and went from esoteric things like building quantum computers and figuring out why the nitrogens and the vacancies behave the way they do, to practical applications that are becoming real right now. So if we go back a little more than 10 years, 10 to 20 years, you found that people were thinking about using diamonds to make room temperature quantum computers. In particular, there were pioneering scientists in Germany that I show here, did a lot of the early work. There were also people at Harvard University, my colleague Mikhail Lukin and his graduate student Lillian Childress, who were doing a lot of the work in that period in the mid-2000s. But there was a problem. Remember how those spins and that magnets change the rate of photons coming out? Okay? That means that you need to carefully control the magnetic field that the diamond's exposed to. Otherwise, you're going to tilt that magnet around and change the rate of photons coming out, and that's an annoying thing that you don't want to have happen. That will mess up your quantum computing signal. So if your magnetic field is in this direction, the magnet would point that way, but if you rotate your magnetic field, it might flip, and then it would change your rate of photons coming out and mess everything up. So that was an annoyance that the people were dealing with at that time, a technical challenge in that period. And so good old Mikhail Lukin was worrying about technical challenges. He would talk to people who came to visit Harvard about this, and people would say, yeah, man, too bad, sorry. One of our colleagues, a man named Dmitry Budker, who was a professor at Berkeley at the time, visited, and he liked to make magnetometers, things that measure magnetic fields. He says, well, if your diamond and these NV centers are so sensitive to magnetic fields, maybe it would make a good magnetometer. What do you think? And Mikhail Lukin wasn't a magnetometer guy or precision measurement guy, so he came and he said, let's ask Ron, because I was the local precision measurement guy who built clocks and things like this and MRI machines. And I thought about it for a little bit. When they asked me, I said, it actually might be a very useful magnetometer, because diamond is hard. It's known that you can put it into biological things without it affecting living creatures. It can go into high temperatures, low temperatures, high pressure, low pressure, radiation. You can cut it into all sorts of shapes, not just gem shapes. Maybe these NVs might be good magnetometers for a lot of practical things. So the three of us started brainstorming. We came up with some ideas. We got our colleague Amir Yacobi involved, who also knows a great deal about studying nanoscale magnetism. He came up with more ideas. By about 2007, we realized this is potentially a very good thing. So we started getting our many graduate students and postdocs, some of whom are listed here and shown, involved in this. They verified that we weren't being crazy and that it might make sense. They fleshed out the ideas, and we all decided to start an experiment to demonstrate whether this would work. So by 2007, we had a little group of students and postdocs. Here are many of them in this photo from that period. I'll come back to this later and show you what they're doing now. And we got it started demonstrating this. Would this diamond actually be a really useful magnetometer? We demonstrated some capabilities, published some scientific papers. The world took notice. By 2010, DARPA, the big funding agency for DoD, decided, wow, this might be useful for various practical applications. So they pumped a lot of your tax money into it. Okay, thank you very much. You may not have known that was going on, but it was. Keep up the good work. Keep paying your taxes, please. The worldwide scientific community began copying us and following our lead, and a lot of people were using these quantum diamond magnetometers for lots of scientific demonstrations, and the number of scientific papers rose and rose and rose. Great, so that's good for the scientists, but you may be thinking, so what? What good is this technology? He keeps telling us he's going to tell us something useful, and so far all I've heard about is photons and pink things and money coming from my tax dollars. Okay. So I'm going to tell you 3 example applications. There are many more, but 3 that are moving into the real world, either to solve basic scientific problems or practical problems today. One is about the origin of the solar system and the origin of life on Earth. It is thought by scientists, with evidence from other solar systems they look at with telescopes, that magnetic fields played a key role in the formation of our solar system. You had a large dust cloud before the sun and solar system formed. There was a gravitational instability, and almost all the mass within a couple million years ended up in the proto-sun with a big swirling plasma dust disk around it. Planets haven't yet formed. The electrical currents in that dust disk, as shown here, created large magnetic fields. Scientists theorize that these magnetic fields created instabilities which may have led to the formation of the planets. That's a nice story. Do we have any record that that is actually happening? Not until very recently. So really people want to know, is this story true, and what were these fields? There's another big question. We know that as the Earth formed, eventually a geodynamo got started that creates the Earth's magnetic field we have today, which shields our planet greatly from charged particles from outer space, keeping it safe for light. When did that geodynamo get started? And do we have any record of it? We do, going back to maybe 3-point-something billion years ago, but did it get started more than 4 billion years ago? Remember, the Earth and the solar system about 4.5 billion years old. Well, we're answering these questions now together with earth and planetary scientists like Roger Fu from Harvard, who dig up very ancient, more than 4 billion year old rocks in places like Western Australia. There are tiny bits of rocks left over from the very early Earth. And they also find meteorites, which fall to the Earth. And by looking at the isotopic ratios and the chemical composition, occasionally they can determine some of these meteorites formed long before the planets did, during the process of the solar system forming, and they are relics from the past. And in certain cases, the tiny iron grains that they have inside them contain and bear the record of what the solar system's magnetic field was as it was forming. And the ancient rocks from Western Australia contain a record of the magnetic fields in the early Earth and help us answer the question when the geodynamo gets started. So in fact, we're answering these questions now using this quantum diamond technology, a microscope in which there's a diamond chip, tiny slices of rock are placed on it, and we can image the patterns of magnetic fields at the micron and nanoscale to try to answer these questions. For example, the Allende meteorite, which fell in Mexico in 1969. It was a giant asteroid. It broke up into a series of boulders as it came through the Earth's atmosphere. The outer surfaces got hot, but deep inside chunks like that, it remained cool. Scientists got these meteorites, they sliced them up, and they began looking inside. They did chemical analysis. They find the parts of the meteorite which look very ancient, that are formed during the time in which the solar system was forming. They zoom in on these areas, they take optical images, and then with the quantum diamond microscope, we can take magnetic images for the first time with the spatial resolution to be able to determine what were the magnetic fields that these tiny grains were exposed to as the solar system was forming. And we now know that these ancient magnetic fields were about 100,000 times larger in interplanetary space than the magnetic fields we see today. And that's consistent with the models and the theories that indicate that these magnetic fields were driving instabilities which led to the formation of the planet. Okay, so these are that's not a practical conclusion, but we're really learning about basic things about how our solar system and planets formed. Now I will tell you about a couple practical applications. One in single-cell medical diagnosis, again using magnetic fields and the quantum diamond microscope. So if you have a tumor cell, you can label it with magnetic beads. You can stick it into a human blood sample, look at an optical image. Can you find where the tumor cell is? No, you can't, because the blood covers that cell. If you didn't have the magnetic bead, you wouldn't be able to find the tumor cell either. But the magnetic fields pass through the blood into the quantum diamond imager, and we can see it. So there it is. With this technology, now we can find all bad cells that are in a sample. And we can move forward by finding all bad cells, all bad tumor cells to save lives. So in fact, there's a startup company whose goal is to commercialize this technology. Compared to all other ways of finding such bad tumor cells, it is 100 times more sensitive to technology, 10 times faster. It doesn't have all the nasty chemicals that are used in other techniques. It's a much smaller device as shown there, and it's 10 times lower cost. Now that sounds like an advertisement, and part of it is because I'm an advisor for the company and I have a financial interest, okay? But I think I'm actually telling you the real story. I need to tell you that. Okay, it's spun out of our laboratories. Okay, last application, navigation without the global positioning system. What is the global positioning system? Most of you know with your phones and in cars, there's a network of satellites sending signals with atomic clocks on board the satellites, and the triangulation of those signals to your phone or to your car allows you to know your position and your motion. It's a wonderful thing. So the triangulation is shown here, where you might have 3 satellites sending signals to you. The signals are coming at the speed of light, time-stamped, but if you're at different distances from the different satellites, the differences in the time of flight let you know where you are, as long as you know where the satellites are, et cetera, and all that information is known. It's a wonderful technology developed by the military and now available to everyone. But that's our military, available for the US. China has their own system, very similar. Russia has their own system, very similar. They all work very well. They're all based on satellites. They're all very fragile. Each country could easily take out the other system if they wanted. So what if the satellites are destroyed? For example, in war, space aliens, asteroids, etc. What would we do? How would we navigate? Not only ourselves personally, but the military. This is a very important question, but there is an answer. We could navigate by the Earth's magnetic field. The Earth's magnetic field is not uniform. It has detailed variation across the surface of the Earth. And for example, if you look at the map of the United States, the anomalies in the magnetic field are like a fingerprint, unique patterns that are unique to each location that you visit. Zooming in on Massachusetts, there are unique patterns. So if you have a magnetometer which is good enough, sensitive enough, stable enough, and you know what those patterns are, you could navigate by them. This idea is not new. People have been attempting this for a long time. The military has as well. And they've built magnetometers on planes and things, but they tend to be too bulky to operate for long periods of time. They're not sensitive enough, and they drift. So a few hours later, a few days later, the ability to tell the directionality has been lost, and instead of navigating in the direction you want to go in, you're going in the wrong direction, or you end up in the wrong location. Lockheed Martin, in partnership with Harvard, has been now developing magnetometers based upon these quantum diamond technology. They put a good amount of money into it and developed magnetometers that are about the size of a Pringles box using diamond, that are already on planes and helicopters and ships and land vehicles and submarines, etc. They're working quite well, and they overcome a lot of these problems that I mentioned on the other magnetometers, particularly because of the crystalline axes within the diamond. There are 4 axes along which you find these NVs, and that gives you a vector magnetometer which doesn't drift because diamond is so hard and so stable. So there you go. That's another real-world application that's moving out and will be available soon to give us the ability to navigate if GPS is taken out. Okay, I've told you about quantum diamonds, and I'm going to end now with a couple little things. One is, where are they today? Remember those grad students and postdocs who did a lot of the work in 2007 and 2008 to start this field off? Here's what they're all doing today. Many of them are professors at schools around the world, and some are in industry, some still doing quantum things, some in Silicon Valley, etc. Jake Taylor, who's up in the corner there, I inserted his picture, is actually the White House science advisor for quantum technology, so it's interesting. Thank you. I'll be happy to answer your questions. You know, an obvious one is, aren't diamonds expensive? You know, I've been mentioning things being practical and low cost, but aren't they expensive? And the answer, I'll start with that, is no. The diamond gems that you buy for rings are expensive. That's because of essentially a cartel that maintains the price very high. Diamonds that are grown in the laboratory en masse for use in applications like this can be at the kind of few dollars each level, or tens of dollars depending on the scale of the manufacturing. So diamonds themselves are not intrinsically valuable. They are as gems because of this cartel. So that is not a limitation to this technology. With further economies of scale, it could probably get down to pennies per diamond. Thank you very much.